Happy learning! Today we're going to talk about Hamiltonian cycles. So let's start by defining what a Hamiltonian cycle is. A cycle or path. Okay, so we're also going to have this definition of Hamiltonian paths. In a graph G, that contains every vertex is called, well, you guessed it, a Hamiltonian cycle or path. Okay, so just recall, what does it mean for a walk to be a cycle or path? It means that you don't repeat any vertices except for the starting one in the case of a cycle, right? You're going to start and end at the same point for a cycle. So recall that a cycle and path cannot repeat vertices. All right, so a Hamiltonian cycle is a cycle where we start at a vertex and we travel to each vertex exactly once except for the starting and ending vertex. That's going to be a duplicate. All right, so we want to travel and hit every vertex exactly once. All right, let's take a look at an example. Does the following graph have a Hamiltonian cycle? What about path? Or maybe it's neither. All right, and so here's the graph. All right, so is it possible to travel along this graph and start and end at the same point and hit each vertex exactly once? All right, so try that. And if you think it's impossible, see if you can start and end at different points, right? That would be a path. Okay, so I hope you tried this. Is it possible to get a Hamiltonian cycle? So can we start and end at any vertex and hit every and make sure we visit each vertex once? And the answer is no. And the issue is this vertex here. Right? If we start on the left hand to the left of this vertex, once we travel to the right of it, we can't travel back without hitting this vertex again. Okay, so this vertex is causing us issues. So we can't have a Hamiltonian cycle, right? Try it. Try to find a Hamiltonian cycle. You're going to find some issues. But we can find a Hamiltonian path, right? If we start here and travel this way, and then we could either go up or down, or be up or to the left, it doesn't really matter. So let's go here and here. That is a Hamiltonian path. We visit each vertex exactly once. So there is a path. All right, but there are no Hamiltonian cycles. We can't find one. All right, what about the following graph? All right, can we find a Hamiltonian cycle or Hamiltonian path on this graph? Now, one thing to note is where these edges cross, that's not a vertex. It's just the edges cross. All right? So the vertices are these ones that I kind of made bolder. And in this graph, it is possible to find a Hamiltonian cycle. Okay, let me show you one. So let's say we started here. If we go here, 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 and then maybe we traveled down, up, diagonal, and back to where we start. All right, and so you can see that we hit every vertex exactly once, and we start and end at the same vertex. So this has a Hamiltonian cycle. All right, so as we see, some graphs don't, some graphs do. We're not going to have a theorem that is as clean as the theorem that told us about Eulerian circuits and Eulerian trails. But we can state a few necessary conditions to ensure that a Hamiltonian cycle is possible. All right, so these are a few necessary conditions. All right, basically, these conditions we're going to state, if any of them fail, then we automatically know that there's no Hamiltonian cycle. All right, so the first one is G must be connected. All right, if we have a disconnected graph, then it's going to be impossible to get from one component to the other. So there's no way we're going to be able to find a cycle that hits every single vertex. All right, condition 2 is no vertex of G can have degree less than 2. All right, so we can't have any degree 1 or degree 0 vertices. There's no degree 1 vertices here, but if we had an extra vertex, that's degree 1, and we would still not be able to find a cycle. All right, and then the last necessary condition, G cannot have what's called a cut vertex. Okay, what is a cut vertex? It's a vertex where if we remove it, the graph becomes disconnected. This is a cut vertex. If we got rid of this vertex and all the edges out of it, we'd be left with a disconnected graph. So a cut vertex is a vertex whose removal disconnects the graph. All right, so I saw that this was a cut vertex, so I automatically knew there was no Hamiltonian cycle. All right, so now we'll state a theorem that tells us when we know for sure that there is a Hamiltonian cycle. And this is called Dirac's theorem. All right, so what does Dirac's theorem say? It says let G be a graph with at least 3 vertices. Okay, so we have a graph with at least 3 vertices. It's almost every graph. If every vertex of G satisfies that the degree of G, the degree of the vertex is greater than or equal to n over 2. All right, n here's the number of vertices. So if the degree of each vertex is at least n over 2, the theorem says then G has a Hamiltonian cycle. All right, so this is saying, right, this is the degree being at least n over 2. That means that there's a lot of edges out of each vertex. And so if each vertex has a lot of edges out of it, it's certainly likely that you're going to be able to find a cycle that hits every vertex exactly once. Now note that this is not an if and only if. It's possible for a graph to have a Hamiltonian cycle and that some of the degrees are smaller than n over 2. In fact, I shouldn't have erased it, but the graph I just erased does not satisfy this, but it did have a Hamiltonian cycle. I'll give you another example. So the following does not satisfy the degree of the vertices are greater than or equal to n over 2, but has a Hamiltonian cycle. All right, and what is the graph I'm going to show you? It's just the cycle with 5 vertices. This graph has 5 vertices. So 5 over 2 is 2.5. Each vertex has degree 2. 2 is not greater than or equal to 2.5. But there is a Hamiltonian cycle, right? Just this. All right, so this has a Hamiltonian cycle, but it does not satisfy the assumptions of Dirac's theorem. But that's OK. So we're now going to turn our attention to a family of graphs that are as connected as possible. These are the graphs with the most possible edges. And so they certainly are going to satisfy this theorem, and they are certainly going to have a Hamiltonian cycle. Okay, a simple graph. Remember what simple means. Simple means that there are no loops and no multi-edges. A simple graph G is called complete. If every pair of distinct vertices are adjacent. There's an edge between every possible pair of vertices in the complete graph. The complete graph on n vertices is called K sub n. I always joke with my class is that graph theorists just don't know how to spell. That's why they use K. But let me know in the comments if you know why they would use K for a complete graph. I suspect it's just K has the same sound as C, but I'm not sure. Maybe it makes sense in a different language. Okay, so what do these complete graphs look like? Well, K1, that's pretty boring. It's just an isolated point. K2 has two vertices, and of course they are connected. K3 has three vertices. Every pair of vertices is adjacent. K4 has four vertices. Every pair is adjacent. And then I'll do one last one. K5 has five vertices. And again, every pair of vertices is adjacent. All right, just a few properties of these complete graphs. All right, the first property is that each vertex in the complete graph has the same degree, and that degree is n minus 1. Okay, the next property is that the total number of edges is n times n minus 1 over 2. Okay, where does that come from? It comes from the handshake lemma that we talked about in the previous video. Okay, so if you look at the handshake lemma and this first statement, you get this for free. All right, try that. And then the final property of Kn that we're going to talk about right now is that of all simple graphs, Kn has the most possible edges. Okay, we're actually going to state one more property, but we need a little bit of notation before we get there. This notation, n factorial, right? N exclamation point means n factorial. This is a number, and it's basically, if you take a whole number, 10, and the way you get 10 factorial is you take 10 times 9 times 8 times 7 times 6, all the way down to times 1. All right, so n factorial is n times n minus 1 times n minus 2, all the way down to times 2 and times 1. Okay, why do we need this? We're going to talk about the number of Hamiltonian cycles on a complete graph. But just so you have an example, 6 factorial is 6 times 5 times 4 times 3 times 2 times 1, which I believe is 720. All right, so this exclamation point means factorial, and it's just this product. And so what does this have to do with complete graphs? Well, given a specific starting point on Kn, So if you say what vertex you want to start on, Kn has n minus 1 factorial distinct Hamiltonian cycles. That's a lot. If you have your calculator out, plug in 20 factorial, and you're going to see it's a massive number. All right, so let me just give you a very quick example. If we were to believe this theorem, which you should, it's a theorem, K4 has 3 factorial distinct Hamiltonian cycles. 3 factorial is 3 times 2 times 1, 6. There should be 6 Hamiltonian cycles on K4. So let's see if we could list them all out. All right, and we'll start in the top left corner. So 1 would be this. All right, and then we could do the same cycle, but in reverse. Okay, another cycle would be down diagonal. And we could do the same cycle in reverse. Okay, and then there's one last cycle, which we could go this way, diagonal here and here, and then we could obviously go in reverse. All right, so these are the 6 Hamiltonian cycles on K4 starting at the top left vertex. Okay, you can imagine K5, there's going to be much, much more. K6, a lot. K7, at some point, even a computer is not going to be able to handle the number of different Hamiltonian cycles, which is kind of crazy. Okay, so that's all I have for this video. In the next one, we're going to talk about finding Hamiltonian cycles with the least weight. We're going to look at weighted graphs and Hamiltonian cycles on weighted graphs. It's going to be very exciting, so you have something to look forward to. All right, take care. I will see you in the next one. Bye-bye.